catalysis, energy storage, and electron emission. So studying these materials can lead to a lot of interesting new findings and new applications. In my lab, we've been focused on 2D electrides, which are the layered version of these materials, and they have layers of these bare electrons surrounded by layers of ions. And so this can give them all kinds of interesting properties. Now, there are only currently 6 2D electrides that are known, and they tend to be they tend to have certain cations incorporated into them. And so you could imagine if we're able to find new electrides, we could potentially find new interesting properties and many new applications. So the question becomes, how can we design new electrides? There are currently 2 predictive features that have been agreed upon for these 2D electrides. The compound electron count needs to be such that you have excess electrons available in the lattice. And then the neighboring cation typically is fairly electropositive. So if we look at the periodic table, we can see that the cations that have been incorporated, which are grayed out in my figure, are very electropositive cations. It has also been shown that the more electronegative cations, so yttrium and hafnium, actually have some amount of electron atom hybridization present in their 2D electride structures. So the question becomes, based on this, is how does electronegativity affect electron atom hybridization? And then how does that affect the electride character of those structures? Scandium is an interesting cation to study because scandium carbide has already been computationally predicted to be an electride. And it's also been computationally predicted to have high hydrogen and storage capacity. So if you were able to make a discandium carbide layered structure, there could be many potential interesting applications. So the phase diagram of the binary scandium carbide composition is relatively, it's relatively old. So it was published about 30 years ago, and it still currently is has 3 different phases. So we have 2 compositions that have stoichiometries of 4 to 3 and then 15 to 19. And then we have one, which is, I'm showing here, has, it can incorporate different amounts of carbon vacancies into an NaCl type cubic structure. And so it would be within this area that we would find a more ordered layered discandium carbide. Given that this is an experimental phase diagram, we wanted to predict how we could synthesize the layered discandium carbide and if it was possible. So we used an evolutionary algorithm to predict stable and metastable phases within this given phase space. And we found that the layered discandium carbide is in fact on the hull and is the most stable structure. And so because it's a thermodynamically favorable phase, we should be able to target this via high temperature solid state synthesis. However, there are many metastable phases that are just off the hull, which might explain why the layered discandium carbide had never been previously synthesized. So we set out to do this synthesis by combining scandium metal and graphite in an arc melter. And then after arc melting, we took an X-ray diffraction pattern and compared it to our predicted phases. You can see in the diffraction pattern, we have on the x-axis degrees, and on the y-axis, we have intensities. And so at 50 degrees 2 theta in the layered phase, even though it's very similar to the cubic diffraction pattern, we have a peak that is distinct to just that phase. And you can see in my observed diffraction pattern of the product, we have a small peak at 50, indicating that we do have some of the layered phase present. However, after doing refinement, we found that the layered phase made up less than half of the product, which was surprising given that it's the thermodynamically favored phase. We hypothesized that because arc melting has a rapid cool down process, we might have kinetic trapping of carbon and be favoring the cubic, more disordered phase over this very ordered layered phase. So in order to overcome this kinetic barrier, we followed arc melting with a 7-day annealing at 1100 degrees Celsius. And the diffraction pattern that we get after annealing shows that we end up getting more of this thermodynamic phase. So we get mostly the layered phase after annealing, and the predicted structure and the experimental structure line up very well, which supports the idea that we were indeed able to make this layered discandium carbide phase. We wanted to explore the effects of annealing a little bit more in depth. So we used transmission electron microscopy, and my colleague Becca Radomski took many of these images. So before annealing and after annealing, we could see that there were different, there were much larger crystal domains after we annealed. So here I'm showing TEM images that have color coordinated crystal domains. And so on the left image before annealing, you can see there are many small crystals, and the Fourier transform associated with this image shows more of a ring pattern, whereas after annealing, we see one very large crystal domain, and the Fourier transform shows a spot diffraction pattern, again supporting that we have very large crystals. So we took an electron diffraction pattern of this very large crystal in the after annealing photo, and we found at this zone axis that the 117 plane is present, and this plane actually aligns to the peak at 50 degrees that I pointed out in XRD that is unique to the layered phase. So what we're showing here is that this very large green crystal after annealing is in fact all layered, which again supports that after annealing, we were able to get much more of the layered phase and that we were able to favor the thermodynamic product. And so we compared all of the predicted structure, the structure from XRD and the structure from TEM, and you can see that their lattice spacings all match up very well, which supports our predictions and again supports that we've made this layered discandium carbide and that annealing did in fact help this process. So now we're able to update the phase diagram to include this layered discandium carbide, and it sits in the middle of this large cubic disordered phase. And so given this information, we now wanted to understand the properties of this new structure. So we wanted to assess the electride character. We compare this to known electride diyttrium carbide, and you can see here what I'm showing is the electron localization function, which shows where the electrons are localized relative to other atoms in the crystal structure. And so you can see here that we can see electrons for both the yttrium and carbon atoms. We can also see electrons that are localized aside from those, and those are the electride sites. And so if we were to see that in the discandium carbide, we would say that that is also an electride. And that is in fact what we see. So we again see this the same structure with the same electron sites. And so it looks like that this layered structure that we were able to predict is an electride. Now, we did say, so this is the most electronegative cation that's been incorporated into an electride. But our question then became, how electronegative can we go and still see electride character? So we decided to incorporate an even more electronegative atom, aluminum, into the same structure and see if we would still get the electride character. And so you can see now in aluminum carbide, we do have some amount of electron localization between the aluminum atoms that I'm pointing out here, but it's not localized in sites in the same way that it is in the scandium and carbide cases. And so our conclusion from this is that there is a spectrum of electride character based on the electronegativity of the cation. And because aluminum is more electronegative than scandium, we see still some electron localization, but not as much electride character as we're seeing in the scandium and yttrium carbides. We wanted to understand how all of this plays a role in electronic structure, because currently all known 2D electrides are metallic. So the yttrium carbide is the only example of a semi-metal that exists in these 2D electrides. So we calculated the band structure for scandium carbide and found that, in fact, the bands do start to split now that we have a more electronegative cation incorporated. So we see a very small band gap in the scandium carbide structure. We measure the conductivity experimentally to see if our experimental structure is also semiconducting. And so we took the band structure and calculated the conductivity at room temperature and got it to be 22 Siemens per centimeter. And then our experimental conductivity at room temperature is about an order of magnitude lower than that, meaning it is still, it is characteristic of a semiconductor, and it's expected that our experimental value would be slightly lower, given that the ideal crystal structure that we have calculated computationally doesn't include impurities or grain boundaries. And so this indicates that our experimental structure is semiconducting, and we have in fact made the first semiconducting 2D electride. We wanted to again explore how electronegativity could affect the band gap. And so we calculated for the aluminum carbide structure what the band gap would be, and found that again, it splits even a little bit more. So now we get a half an AV band gap. And so our conclusion here is that based on the electronegativity of the cation that you're incorporating into these structures, you can actually tune the band structure to get anywhere from metallic structures to wider band gap semiconductors. And that's what we're showing here. Lastly, we wanted to explore the discandium carbide stability in air, as electrides tend to be fairly unstable. So we did this by doing XRD of the product after sitting in ambient conditions for a set period of time. So we did this over a month and took diffraction patterns at various time points. We found that as the product sat in air, our crystallinity of the peaks decreased, and we end up getting much less intensity, much broader peaks, indicating that it's forming in an amorphous phase. So we wanted to explore the mechanism of oxidation. So we used X-ray photoelectron spectroscopy to understand oxidation on the surface of the material. And you can see before any oxidation occurs, we have very nice peaks for both scandium and carbon, indicating that we have scandium carbide present, and then some amount of scandium oxide or adventitious carbon. After 1 day in air, we have a decrease in the intensity for the scandium carbide peaks compared to the scandium oxide and adventitious carbon peaks. And by the 11-day time point, we see no evidence of any scandium carbide left in, on the surface. And so based on this data, our conclusion is that we have an amorphous oxide forming on the surface of this material first. And as we continue to let it sit in air, the oxygen continues to diffuse into the material, and eventually the bulk of the material turns into an amorphous oxide. So in conclusion, we've done a few things through this project. We've now incorporated the most electronegative metal into next to the electride site, scandium. And so this pushes our understanding of electride design rules and allows us to come to an understanding of how electronegativity of the cation affects the electride character. This is also the first 2D electride to exhibit semiconducting behavior. So this creates an entire new class of materials that have many new interesting applications, such as for battery electrodes, for IR photodetectors, and in catalysis, among other things. The experimental realization of the structures will now allow for the exploration of its very high hydrogen and storage and fluoride storage capacity that were predicted computationally. And lastly, when using this in any of these applications, passivating coatings will need to be used as it is sensitive to air. So I'd like to thank you all for coming to my talk tonight. I really want to acknowledge all of my co-authors, my PI, Professor Scott Warren, my funding sources, the NSF and the GRFP, along with the instrumentation at the UNC Channel facility. And I'll let you know, I'll give a plug for our paper on Chem Archive, and I'll take any questions.
Any questions for Lauren?
Oh, hi, Lauren. It's a very nice talk. I do have a small question. So this is definitely not my field, but so I apologize if the question is not like technically right. But so anyway, so you mentioned that you have some defects, which leads to that the actual value was far from predicted. So is this defect more referred to the surface defect or any impurity dopant in your semiconductor?
It's probably, so as I showed from the XRD pattern, we have a 15-ish% of the cubic phase, which is does not have the same conductivity as the layered phase. And so that impurity is present in this experimental sample. And so I think your second point is right on. We have impurities present in the sample that are affecting the conductivity.
Okay, thank you.
May I have two questions? In your slide 7, the seed scale bar. You have the scale bar in the seed, in the select electron. See that?
For some reason, it made me stop sharing. Let me try again. Okay. This slide here is what you're referring to. This slide here.
7. Yeah. I see 5 per nanometers. That 5 nanometer is 5 per nanometer. Does this mean your scale bar is 0.2 nanometers?
Yes, that is correct. Yeah, because this is in reciprocal space.
Okay. And also I heard you mentioned this phase 1 to 0, this Miller indices. So these ones, are they favorable to be formed?
Sorry, what? I don't think I understand the question.
Oh, sorry, sorry for my Chinglish. I mean, that different plane, is that plane is orientation occurs?
Yeah, so the 117 is the one that's unique to the layered phase. The 120 we see in both the cubic and the layered phase. So that one, yeah.
Okay. And also I heard you mentioned your sample scandium carbide can be used for battery electrode.
Yes.
So that's so for electrode or electrolytes.
So we are a lot of my research has actually been going into trying to incorporate these into fluoride ion battery anodes. And so you could imagine, and we actually have a paper out about this, but it's for Y2C when we mentioned scandium carbide, but it had not been synthesized yet. So you could imagine replacing the electrons in the layered structure with fluorides. And there's a huge potential for energy storage, but there's not a huge change in lattice spacing. So there's only really a 5% decrease in the lattice size. And so it's very useful for a battery anode because fluoride ion batteries do not yet have intercalation anodes, and conversion anodes tend to degrade really quickly. And so this material could be really useful to kind of fill those needs as a battery anode.
My second question is corresponding to Wenshao's question. How do you improve the conductivity experimentally?
Yes, so what we're trying to do now is increase the purity of the sample. And we think that the reason we still have some amount of the cubic phase is because we're getting oxygen into the sample. So during like transfer processes and even like during annealing. And so we are now trying arc melting with titanium, which will kind of suck the oxygen out of the arc melting chamber. And then we're also going to try annealing with titanium in the tube in order to make sure that we're purging the entire environment of oxygen to favor this thermodynamic phase. And that way, any of the impurities will hopefully be taken out. So that's kind of our next step in trying to improve the purity of the sample and getting the conductivity a little bit closer to what we're expecting from computation.
Okay, so that conductivity is a dry conductivity or white conductivity? It's a dry one.
Yes.
Okay, I think we have one more question from the chat box. Do you want to check it? Or Sarge, do you want to ask it?
So I see in your TM images, you said something like Fourier transform. Does this mean you measure the signal in time domain and transform? Yep, that's exactly what it is. because I'm not a TEM expert, Becca, who I mentioned here is, she would be able to explain it a little bit better than I, but what you just said is exactly what she does. So this is a Fourier transform. So we're looking at this in a different space. And then the second question is the software to predict viable structures using an evolutionary approach. It is public domain or something the average group? Yes, so we use USPEX, which is probably, USPEX and Calypso are the two most popular algorithms to use for predicting crystal structures and predicting phase diagrams. USPEX is proprietary, but you can get it pretty easily. They have, so they don't show their code, like it's not on GitHub, but it's very easy to use. And so if you were to buy it for your group, you would be able to, and you can interface it with different DFT methods. So we use it along, so it's really just structure generation along with structure optimization. And so you have to use DFT to optimize the structure. So we use VAST. And you can use it with any type of structure optimization method. So there are other ones out there that people use. So it's really easy to use, but it is proprietary. So you won't be able to read the code itself.
Hey, I have a question. Can I ask? Regarding the after annealing, there are different d-spacing. Is all, I have a question. All this d-spacing is belong to SC2C or no?
Yes, so all of these, so these spacings do. The TM comes from the electron diffraction patterns. The XRD comes from the X-ray diffraction patterns of the layered scandium carbide, and predicted again comes from the layered scandium carbide that we predicted computationally.
Okay, no, my question is, you know the picture, the photo in the green bars? The green lines are different d-spacing, which means there is, I believe, there are another metal.
There, excuse me, I'm sorry. I don't know if I'm understanding.
After annealing, there are plenty of different d-spacing in the TEM image, which are not the same.
Oh, I see what you're, so you're saying that there are different crystals that are all in green, or different crystal domains. So they're actually the same lattice spacings, they're just oriented differently. So we have slightly different orientations, but they're all part of the same crystal. And I think they're overlapping, but they're 60 degrees from one another, which means that they're all part of the same spacing. They all have the same spacing, so.
Okay, thank you.
Yeah.
Any other questions for Lorraine? Any other questions? 3, 2, 1. I assume no more questions for Lorraine. Let's give her a round of applause. Thank you, Lorraine. Our next speaker is a gentleman, Mr. Wenhao Shao. Wenhao is also a PhD candidate. He is under the supervision of Dr. Jian-Sang Kim from the University of Michigan. Wenshao's research focusing on the organic semiconductors and the light emitting devices. So Wenhao is also very active. Recently, he just presented in the 40 years anniversary to celebrate Chinese American Chemical Society Foundation. Yes, so Wenhao has been presented very well. One professor mentioned, among all these speakers, that young student did the best job. I want to congratulate you, Wenhao, and represent the young generation very well. So in Dr. Kim's group, they have been working on the original design rule for POP. Wenhao will tell us what do you mean by PVP, POP, involving in dynamic symbolysis of the heavy atom effects and orbital angular momentum manipulation. Without further ado, Wenhao, the microphone is yours.
Okay, thank you very much, Dr. Liu. That was a great honor, and thank you for organizing this symposium. It's very nice to be here, and thanks for everyone for being here. So the topic, actually, let me share my screen first. So the topic I'm introducing today is a topic on the so-called metal-free organic phosphorus. So it's a purely organic material. We intentionally don't want any metal to be included for the purpose of, these for the performance of these materials. So let me give you a very short introduction about, the what we have before before introducing the topic I'm introducing today. So, in electronic devices that give out light, we care a lot about harvesting so-called triplet acetons. In organic materials, in organic materials, we care a lot about this like acetone because like electron and hole, they are very deeply interacting with each other, and we cannot really separate them very well. So when acetones are forming, there are two different regimes. One is called singlet acetone and so-called singlet states, and another one is the triplet states. And these turn out that in the organic-based electronic devices, triplet acetone are very important. And first of all, the generation of triplet acetone is you should take a little bit detour from the singlet domain, which involves a mechanism so-called intersystem crossing, involving the population of triplet states from the singlet states. So the acetone needs to be moved from a singlet state to triplet state. And then you have to worry about how to let this triplet acetone emit the light. So when it emits light, we usually call that phosphorescence. So phosphorescence is all about the business of how you protect the triplet acetone. It turns out that these acetones are going through a so-called spin-orbit coupling process, which makes their lifetime are a little bit long. And by long, I mean in the order of millisecond and even seconds sometimes. So when your lifetime is very long, you need to worry about how to suppress your non-radiative decay, because that's because your emitting process, your radiative decay process is always competing with your non-radiative decay process like heat. So how to suppress that, and at the same time, how to enhance your intersystem crossing rate and your phosphorescence emission rate is very important. And people generally use two different strategies. One so-called heavy element FET, another one is how to manage the orbital angular momentum. And this I will explain in the next slide. And conventionally, when people design phosphorescence materials, people use organometallic complexes, and they involve heavy metal. And this is what I'm talking about, the heavy element FET. And you see, because we're using metal, the atomic size is really, really, really big. So they can have a very great heavy element FET, which cause the lifetime to be very short of these triplet materials. And the triplet acetone is not that long-lived. They can be falling into the regime of microsecond, but they do have a lot of issues like cost and stability issues, especially when you're talking about higher energy acetones. So our group is very interested in developing so-called metal-free, purely organic phosphor, and that's where this word POP is coming from. And we do need some heavy atom, and instead of using a metal, by removing the metal, we have to use organic derivative of heavy atom, which is usually bromine, iodine, or recently we use selenium in our group. And because they are not that heavy, and usually our lifetime of the phosphorescence material are usually pinned in the millisecond, even to the second regime. And for these materials, because their lifetime very long, you really need to worry about how to suppress your non-radiative decay. So throughout the previous decade of the development of POP in our group, we achieved a lot of system to engineer how to engineer your environment, your matrix, so that you can suppress the non-radiative decay. For instance, when it first came out, we designed crystal system, and later on we moved to amorphous polymer, and they are much easier to fabricate compared to crystal. Generally speaking, phosphorescence materials or POPs, they have two directions. One, intentionally you make the lifetime really, really long, and they are really good for sensors, and we call them ultra long phosphorescence. And another direction, we make them very fast. in terms of electronic devices, because electronic devices, you have a certain phenomenon called device blow off, which means that when your triplet lifetime is really long, they ultimately will kill your device because they cannot be removed by emitting the light in a very fast fashion. So our contemporary POPs people have designed these years. For instance, they usually have this certain kind of structure. For instance, we usually use bromine to induce heavy atom effect. And we do need another agent to satisfy so-called angular momentum difference, which I will introduce later. And you can also fully remove heavy atom, and they tend to give a lot longer lifetime in the second to hundreds of millisecond regime. And okay, so in terms of how to populate triplet states and how to let the triplet state emit the light, there is a phenomenon that's super important called spin-orbit coupling, because the electron needs to flip its sign during the emission process or the population of triplet state process. So the spin-orbit coupling is directly related to the rate of spin-orbit coupling is related to this in quantum physics related to this Hamiltonian, and this HSO here is so-called spin orbit Hamiltonian. And it is related to many different descriptors, but importantly, we need to know, for instance, we have a Zn right here, and this R, which is the orbital radius, is also related to the to the atomic size. So ultimately, you are looking for somewhat forced term kind of relationship between your spin-orbit coupling energy and the atomic size. So that's why the heavy atom effect is really important, because spin-orbit coupling efficiency is very sensitive to your heaviness of the nucleus. There is also a bunch of different, you see the L and the S, which stands for the orbital and the spin angular momentum. So I will explain what these means. And basically, we know the very fundamental physical law is that we need to conserve the total angular momentum during any process. And because during spin orbit coupling, let's say your triplet asymptote, you needed to emit the light, which involves an intrinsic spin flip process. So your spin angular momentum has changed. And to conserve the total angular momentum, you have to use another way to compensate that, which is through so-called orbital angular momentum change. So, which is very well stated in the well-known El Said rule. And so how can we visualize this orbital angular momentum change? So for instance, in the very popular BR6A phosphorescence, excuse me. So in the very popular BR6A phosphorescence material, in its, let's say, the HOMO -1 to LUMO transition, which is going to affect the spin orbit coupling from the T2, the second triplet state. From the second triplet state to the ground state. And this actually from the calculation has a somewhat large spin orbit coupling efficiency, which is because you have certain kind of in-plane, which is in-plane electron in the hole and out-of-plane electron in the z direction in the electron orbital, which is the LUMO orbital here. So this in-plane, basically, orbital angular momentum change, well, it's basically the right-handed rule. So if you are rotating, like 90 degrees, you are getting a very large orbital angular momentum change or angular momentum change in general. So this in-plane to out-of-plane change is going to induce a very large orbital angular momentum change. And that is the reason why for this specific HOMO -1 to LUMO transition, you are getting a somewhat large spin orbit coupling value. Typically, but unfortunately, people don't really talk about like angular momentum, because although I make it very clear how to visualize that, somewhat clear, maybe, but generally speaking, it's very hard to visualize that. So usually people, so throughout these years, when people design POPs, purely organic phosphorescence materials, their kind of library of this so-called functional groups that can induce orbital angular momentum change is really limited, usually to carbonyl or some moieties that can induce this in-plane to out-of-plane transition by introducing some non-bonding electrons. So what is missing here is, importantly, for our interest, we are very interested in a certain way to combine heavy atom effect together with the orbital angular momentum change business. So we hypothesized that by the form of this equation, it's very important that your heavy atom, let's say bromine, needs to be in close proximity to the orbital angular momentum change. So for instance, in the orbital I showed before, for instance, if this, let's say if bromine is contributing to the in-plane to out-of-plane change, then you're somehow using a heavy atom to directly inducing orbital angular momentum change. And wouldn't that lead to a very large spin-off coupling value? We are very interested in this because people have been designing POPs for years, but there has not been a very systematic way to increase their spin-off coupling value. And that's why it's very hard to make purely organic phosphors giving a somewhat fast phosphorescence in having a very short lifetime. So having this in mind, we are trying to, our goal is how to engineer the molecular structure so that we can put heavy atom, we can use heavy atom to directly induce the orbital angular momentum change. And we first taught this heavy atom oriented LSI rule, or more precisely heavy atom oriented orbital angular momentum manipulation. And we actually almost discovered this years ago when we studied bromine's position and how if bromine's position relative to the carbonyl group, which can induce orbital angular momentum, and how this position change will lead to different intersystem crossing of phosphorescence. And we found that when bromine is in very close proximity in the ortho position to the carbonyl group, this will give us the highest rate. But we failed to summarize that the reason for that is actually, when I looked back into this paper, I found the reason is actually because here you see this orbital here is contributing from bromine, and the contribution is from the in-plane of the bromine's non-bonding electron. And because it's very close to the carbonyl, so that the non-bonding electron got interacted with the carbonyl's non-bonding electron. And in this HOMO orbital, it is going to the out-of-plane direction. So this HOMO -1 to HOMO transition will give a very large spin-off coupling value, which affects the intersystem crossing phosphorescence rate of this type of material. And also in a very previous report, we also studied how to use selenium to directly induce a in-plane to out-of-plane orbital angular momentum change. And selenium is just one atomic number lower than bromine, so it is actually very heavy. And from our DFT calculation, very simple DFT calculation, we found that the spin-off coupling value is very large. And so we, at this point, we kind of wanna systematically study this and show people that this is actually really working. And we want people to see and use our strategy and design a new strategy to design POP materials and systematically making their spin-off coupling very large. So we taught this HAM, so-called HAM concept, which stands for heavy atom oriented angular momentum change. At this point, we definitely cannot just stick with very simple DFT calculation. So we reach out to our collaborator, Professor Zimmerman, and my direct contact, Han Jie. So their group is specialized in the so-called restrictive active space spin flip, which is a wave function method which gives a more precise representation, interpretation of the angular momentum effect and the spin-off toppling in general, which is a very nice calculation package. And we can get very accurate representation of what is actually going on over there. We designed our molecule series to have a so-called band geometry. And in this specific molecular scaffold, because it's bent, so originally, if it's fully conjugated, it's fully planar, then the non-bonding electron of the selenium, which is a heavy atom, will be fully conjugated with the surrounding pi system. But because it's bent, the p electrons from the selenium somehow get deconjugated, and they are now so-called non-bonding electrons. And in the T1 state of this, in the first triplet state of this so-called SEN, because we have nitrogen here, the T1 to S0 transition is being characterized by a PZ to PXY, or out of plane to in plane transition directly concentrated, centered on the selenium heavy atom. And from the calculation, we have a very large and super large spin-off coupling value among purely organic materials. And more importantly, when you get some spin-off coupling value of more than 100, you are expecting a very fast lifetime in the microsecond region, not in passing the millisecond region. So we actually made this material and we doped it in polymer to visualize its performance. And we found that while it emits very bright phosphorescence towards a quantum yield of 19% at room temperature, its lifetime is only 385 microseconds, which is kind of fast, which is actually very fast among purely organic materials. So later on, we are trying to design a series of experiments to verify this so-called HEM concept through experiments and through computation. And first thing we did is thinking about if we can kind of fix the orbital angular momentum change while altering the heavy atom. So we choose the same molecular scaffold and we replace the selenium with sulfur, which is one row down in one row up in the periodic table of elements. And we found that its overall performance is getting much lower and the lifetime is getting much longer. This is about 2 magnitude longer lifetime. So this is very expected. What is very hard to do is from the other side. How can we fix the heavy atom? We choose selenium, but so we know that for this material, the bending angle is very important to induce non-bonding electron from selenium. And can we somehow decrease this bending angle so that the orbital angular momentum doesn't change a lot, right? So it's very easy to achieve this through computation. And we basically fix the molecular structure while we fix the bending angle during the computation and do the geometry optimization. And as expected, we saw that from 10 to 60 degree bending angle, we have a much larger increased spin-off coupling value. But how to realize this in experiment? You definitely cannot take a molecule and bend it in experiment. So what we are looking at is how to change the bending angle by changing the atom on the other side of the heavy atom. So originally we are starting with nitrogen and we replace this nitrogen with either oxygen, boron, and carbonyl. So let me quickly introduce this to you. So for instance, you know that nitrogen is preferred to have a sp3 hybridization in this type of material. And that's the reason why this molecule is bending. When you switch to boron, which prefer to have sp2 hybridization, you would expect this molecule to be much more planarized, which actually has a much smaller dihedral angle of 8 degrees. And when you switch to carbonyl, which should be much more planarized, right? So actually from the expectation, we have a dihedral angle of around 0 degree, right? So and also when we gradually change dihedral angle from higher to lower, from the computation, we are seeing gradually decreasing similar toppling value. And note that this is in the log scale, so it is actually decreasing a lot. Experimentally, we synthesized all these materials, both in their selenium derivative and the sulfur derivative. And we found that as we gradually move from oxygen to carbonyl, larger dihedroangle to smaller dihedroangle, it generally followed the trend that the K, which is the phosphorescence rate, is decreasing. And at the same time, which the trend is not that pronounced in the sulfur derivative, but generally follows the prediction. And we divided the phosphorescence rate of the selenium derivative by the phosphorescence rate of the sulfur derivative. And we get, this is how we characterize the effect from replacing the dihedral angle, how much gain you will have in terms of phosphorescence rate. And we found that when you have a larger dihedral angle, which means a larger angular momentum change, you will have a larger gain from replacing your heavy atom with an even heavier atom. So in this way, we think we pretty much form a very sound story. And so we write this manuscript and then submit. But for us, we should know that the HAM concept, although we only kind of presented the phenolphthalein derivative, it actually can be used in various molecular structures, because the key concept is how to use your heavy atom to directly stimulate a certain change in the orbital angular momentum. And in our own design, we actually found that you can apply this concept in terms of molecular design in many different ways. For instance, you can use it not just in the chalcogen-based heavy atom-based materials, you can use it for halogen-based, like for instance, bromine, and you can put bromine in adjacent to conventional delta L, the conventional moieties like carbonyl, it can induce optical momentum change. So bromine will have certain contribution to the angular momentum change of the carbonyl non-bonding electrons. And there are many ways you can design that. So we are definitely not just strictly confined to one molecule derivative only. So we do have the manuscript is not published, but we have a preprint available. And if you're interested, I will be very happy to share this with you. So I will conclude right here, and I would like to thank our group, especially my advisor, Professor Jing-Sang Tian, and my collaborators highlighted here may not be actually contributing to this project, but they are contributing to my PhD work previously. So I'd like to highlight them. And also very special thanks to our funding agencies, especially the funding agency for this topic, from NSF and from Samsung GRO. And thank you very much. And I will take any question if there's any.
Any questions for Wenhao? Yunlong, please.
Oh, okay. Can you hear me?
Yes.
Because
Hi.
I'm using airport. Hey, Wenhao, thanks for that's really very interesting talk. I really enjoyed.
Thank you.
Although I studied photochemistry, I really don't quite understand the spin orbital coupling. I think you did a very good job explaining.
Thank you very much.
And also, you mentioned the Nicholas Tudor's book. I actually had it. I think it's a good time to review it. I have a question about, I think at the very beginning, I don't quite understand why you spend all this effort studying this phosphorescence. What's the application of this?
Oh, yeah. Go ahead.
Yeah, it sounds like increase the lifetime earning, but earning just a couple of seconds, and earning also for the LED. What's the commercial application of this studying this phosphorescence?
So Yeah, that's a very good question. So the bigger picture of this material in general, as I mentioned here, that people studied a lot about their, sensor applications where they intentionally made the lifetime of this purely organic phosphorus very long. And our interest is more like from the fundamental side, how can you make the lifetime faster by engineer the intrinsic spin-off coupling? And that's very useful for emitting devices. It's very long been considered that purely organic materials, when you don't have metal, phosphorescence material, they won't have a bright future in organic devices. But we cannot just buy it, right? So in our case, so first of all, for emitting devices, it's very important that you make the emission fast. And first of all, emitting devices, we know that it's a different mechanism compared to photo excitation. In the electro excitation case, at the beginning, when your free electron and free hole, uncorrelated electron and hole, they are combined in your emissive layer, you get 75% triplet acetone in the beginning. So it's very important how to let those 75% triplet acetone to emit the light. So for instance, we might have heard the phenomenon of thermally assisted delayed fluorescence, TADF, which is one way where you originally have the triplet acetone, but instead of letting it go down through phosphorescence, you let it go up and emit through fluorescence pathway. And in our case, we are interested in how to make the purely organic materials giving very fast phosphorescence and how to apply them in light emitting devices. And actually, we have already have a few prototype emitting devices, not just our group, people in this field develop in general to use this POP in emitting devices. And we're not there yet, definitely, because their lifetime is still pretty long. So that's exact question we are tackling in this project. I hope that answers your question.
Okay, thank you very much. Yes.
No problem.
Wenhao, there is a question from the chat box.
Yes, actually, let me read the question. So could we apply the HEM concept in the opposite sense to promote up conversions for organic materials? Yes. So recently we wrote a proposal to NSF where we also described how this concept, we can use it for TADF material, which involves the up conversion back to the singlet state. You can do that. And in fact, this leads to a more important question, how to do so-called state-specific engineering. So people usually consider that when you increase the spin coupling, you increase the spin coupling of everything together. But for up conversion, you kind of intentionally need to shut down the phosphorescence route so that the T1 to S0 spin coupling needs to be very small, but T1 to S1 needs to be activated and to be very fast. And it is very hard, but we do propose some way that we can engineer the material structure, put in certain functional groups so that it can somewhat like realize this goal. But we're not there yet. But this is definitely a very important question. Thank you very much.
I may have a couple questions, if you don't mind.
No problem.
In this slide 2, you do have the singlet excitation and the triplet. What are the differences? What's the reason to result in these two different singlet and triplet excitation?
Yes, it's about how you, so we know, for instance, let's look at this diagram here. We know that from the ground state wise electron, they are paired, but upon excitation, electron doesn't like to flip because that takes a lot of time. And we know from spin coupling, you need that to be very efficient. So very naturally from excitation, from photo excitation, you are moving it up to the singlet state. It's called singlet because the electron and hole, they are still anti-parallel to each other, right? So that's called the singlet acetone. And now if we have efficient spin order coupling, we can flip this electron so that it will stay parallel with the triplet atom. I think there should be a animation right here, which is actually showing the anti-parallel fashion. But I mean the parallel fashion. If it's parallel, we call that state the triplet state. And because of the nature of this spin flip, this takes time. So when triplet atom emit light, it will generate phosphorescence, which is very long lifetime.
Thank you. Can you
sure.
go to your slide 4? Slide 4. I may, yeah, this HSO represent coupling efficiency. Do I yes. My question for you, you do mention 2 factors, the R, the orbital size influence, and also the angular momentum quantum number influencing. My question for you, is the magnetic moment quantum number affecting on the coupling effects?
Oh, that's a
thank you.
Yes, that's a great question. From the form of this equation, only orbital angular momentum is affected, not the magnetic. I actually don't know how to answer that, but actually one fact is that you can use external magnetic field to induce a higher spin of the coupling. That is a fact, and people publish that. Yeah, I hope this answered the question somewhat. But naturally, it's not included in this equation.
Okay.
Mm-hmm.
In the couple more slides, you mentioned the bromine, bromine atom. When you this one, I did see you have different structures. My question, do you think the sp3d2 hybridization of your bromine can occur?
Mm-hmm. Yeah, it does. So for instance, if you look at the molecular orbital and you go from, let's say you first start from the HOMO and LUMO, and then you go a few more slides like LUMO plus N or HOMO minus N, you will see like sp2d and those orbitals in the bromine contributing, but they are very higher lying energy states. So they don't contribute to, emission process. Yes.
In this slide, so the carbons, they take sp2 hybridization, is that right?
Yes.
And then you do have a pz electron, like a, how do you say that, like a pi stacking effect?
Yeah, right.
Right,
so, yes, just one comment to that. Yeah, usually in organic materials in their so-called like lowest excited state, we only care about p orbitals. We don't actually even care a lot about s orbitals unless they are indeed having a very low energy.
Yeah, that's very critical. Thank you, Wenhao. And there's another one in your slide 16, I believe. I do remember you mentioned you have nitrogen, oxygen, boron, and the carbonyl. The boron will be electron deficiency, right?
Yes.
You have 6 electrons. My question is, does this electron deficiency have some impact?
Oh, thanks. So this is not, like the main part of the story, but so it doesn't affect our explanation in the Ham concept, but it does have some impact on the property of the emitting property of this material. It turns out that there are indeed some certain amount of charge transfer from the electron-rich selenium or sulfur to the electron-deficient boron, even if they are just within the same molecular structure and they are so close, which leads to that this material having a very small singlet triplet gap, so that it does have certain thermally assisted delayed fluorescence property that at room temperature or at a little bit high temperature, the triplet acetone, once it's been populated, it can populate back to the singlet state of this material and emit delayed fluorescence. And we saw that in this material. However, for our case, or you might want to ask this question, you are seeing delay fluorescence, then how could you characterize their phosphorescence property? Because all of these phosphorescence rate are measured at 78 Kelvin at very low temperature, where thermal assistance is not going to happen, and we are only seeing phosphorescence. So when we present the values here, they are representing their phosphorescence property.
And if you see your figure D, D, oxygen has more electrons, right? Theoretically have 2 lone pairs. Nitrogen has 1, and the boron has electron deficiency. Carbon supposed to be more negatively partially charged, positively partially charged, right?
Yes.
Because I'm thinking, that didn't show the more electron, the higher the angle, but you show a little, can I say like a volcano? So why this happened?
So the more importantly, so there are 2 effects parallelly going on here. So first is the dihedral angle is different, and that is because you are substituting nitrogen with boron, and which tends to form sp2 hybridization instead of sp3 in the nitrogen case. And that changed your dihedral angle a lot, which is very dramatic. That's enough to overshade all other effects that will really greatly affect your spin photocoupling value. And you are right about the electron, inducing effect right here, that oxygen compared to nitrogen, it may going to donate more electron to the system. And we are seeing that, for instance, purely from the computation, the oxygen derivative has a smaller dihedral angle compared to the nitrogen derivative. And usually we will predict that the oxygen derivative will have a smaller spin photocoupling. But that's not the case. If you look at the spin photocoupling here, the oxygen derivative is actually having a little bit larger spin photocoupling value compared to nitrogen. And we think that's because oxygen is donating more electron density to the total system. Then when you are experiencing a spin photocoupling, you have more electron, and certainly you will have a larger spin photocoupling value. So we are having something you suggested. So that's a very, very good question. We definitely include that discussion in the manuscript, but it's just for the sake of time, I didn't discuss that in much detail.
Wenhao, there's one more question from the chat box.
Okay. Let me see. So the question is, yeah, I can read that. So how accessible is your DFT code, and how easy it is to apply to general geometry and the energy states to understand T1 to S0 and T1 to S0 coupling, and T1 to S0 and T1 to S1 coupling, or does one need deep expertise to undertake these computations? So we're not doing these. I did this all by myself using DFT, but we didn't use that result in the final manuscript, and we choose to use more accurate result presented from our collaborator from Professor Zimmerman group. They have this specialty in the wave function method, which is more accurate compared to DFT. DFT is density function, and their method is based on wave function, and which takes more time, and which involves, from what I understand, which involves a lot of coding and customized way to represent, to write a code to describe this spin photocoupling process and to interpret the result. And I believe their code are available if you contact them. So, but it does require a lot of specialty. I personally cannot do that by myself. So actually here, so many credit to them as well.
Any more questions for Wenhao? I assume the silence meaning no. Yeah, thank you so very much, Wenhao, for your beautiful talk.
Thank you.
Yeah. Let's give our both speakers a round of applause. Yeah, thank you all. Yeah. If any students wish to give a talk, feel free to email to me. If you're not a student, you're a postdoc or junior faculty, junior scientist, also feel free to contact me or Yunlong, either Yunlong or myself. Yeah, feel free to contact us, and then we can arrange some talks for you to showcase your research data. And also the division is going to provide a little trophy for our speakers. And then Wenhao, don't forget to email me your postal mailing address. I do have it unless you change it. So yeah, again, if anybody wants to mingle with each other, I will leave this portal open for a little while, for 20 more minutes. Otherwise, feel free to leave. Our talk officially finished. The meeting is adjourned, but feel free to stay for social. You know what? I have a question for everybody. Maybe just turn your audio, video on. Feel free to say something, to say a few words, or to mingle with your fellow students. We have our previous student, the Spark student winner, Remy. Remy is here. I think we have Daki, who is also giving a very nice talk during the student presentation award competition. Yeah. And we have Joaquin is going to give another talk, I believe in November, is that right? November, yeah. Yeah, Remy, do you want to say a few words?
Yeah, hi everyone, and I want to apologize. I was in commute, and my cell phone was in my pocket. I was listening to the talk while I was in commute, so sorry about that. I'm Roman. I'm a fourth-year graduate student at University of Iowa, and my primary research is on fuel cells. So I'm actually investigating the intermediates for the direct methanol fuel cell, and I'm using spectroelectrochemical techniques. So basically, I'm doing electrochemistry on the surface, and then watching the surface with infrared measurements, infrared techniques. So, and I'm using PMIRS and IRS and SSG sound frequency generation. So, yeah, that's me. Thank you.
Thank you, Remy. Yeah.
Nice to meet you, Mr. Ramin.
Yeah.
Thank you very much. Sorry, I messaged that one. I'm really sorry about that. I messaged, please unmute.
Oh, no, that's totally fine. Actually, several people messaged me, and I was really ashamed because that happened by mistake. So sorry about that. Sorry for the inconvenience.
Yeah, do you want to say a few words? Is that Walid? How do you pronounce your name?
Walid.
Walid.
Yeah, my name is Walid. I'm working on hydrogen production from bio-oil derivatives for about 11 years now. And now I moved to the pyrolysis of plastic waste to produce a valuable liquid fuel, also using catalysis reaction and cracking and reforming, both at the same time. If you want to, can I share something?
Yes.
Okay, share screen. Okay. This is my ORCID ID. Yeah, you may check out later if you want to collaborate or contact me. There are plenty of papers which I'm the corresponding author, and you can find my email address in here. Actually this work are 35, but I have 46 which are not still not online yet. So this is my work. I graduated from Malaysia, University of Technology Malaysia, about 6 years ago. and I'm doing the postdoc at the moment for about 4 years. And I'm very happy to have this sort of network and on meetings which Dr. Jingbo invited me for a few months. Really helpful because I could build my own network with other researchers, not only in Malaysia and in Iran, but other countries as well. Thank you everyone.
Welcome, welcome. Do we have Zahir?
Yeah, I am Zahir Masood. I am PhD student, like PhD candidate, 5th year candidate in Department of Chemistry at Southern Illinois University, Carbondale. And I work in CO2 electrochemical reduction through DFT, like using DFT. And I also work, I have some few projects on oxygen evolution reaction. And I work, recently I have completed few projects on D-metal complexes as catalyst for CO2 reduction. Now I am working for some spinel-based oxygen evolution catalyst. And now my next project will be CO2 electrochemical reduction using first row transition metal oxides. And
do you want to give a talk in our student, we call the student seminar series?
No, I have something to present, but I have to organize. That I have to reorganize. Most probably in sometime in November, I can do that.
Okay. Yeah, I write it down my email in the chat box. Feel free to email me.
I will contact you. So.
Mr. Zahir, sorry, where are you from exactly? Sorry for that, but just
exactly. I'm from Pakistan. I'm from Pakistan.
No, I mean the university.
University. I'm in Southern Illinois University. I work with Dr. Ching Finga. He is a big name in catalysis.
Nice to see you.
Thank you. And I have some experience in electrochemistry, practical electrochemistry. I have some background, some practical electrochemical studies. So that's I had something in my mind that working at the interface on the electrode. So first I need to study about homogeneous system, how it works. Then I move to heterogeneous system, how it works. I have some experimental work in electrochemistry. So in future, I will try my best to dig something on interface. That is very important in the future.
Wonderful. Thank you. Do we have a, can I say Deki, Nishori? Hello, yeah.
Hello everyone, I'm Daiki Nishori. I'm from Japan. I'm in the 4th year of chemistry PhD, and my research is related to the hydrogen production using a semiconductor integrated with molecular catalyst. And also I'm working on the oxygen evolution reaction using the homogeneous molecular catalyst. Nice to meet you all.
Yeah. Thank you for giving a beautiful talk in our Spark.
Oh yeah, thank you so much. It was a very great opportunity for me.
Yeah, and then I will collect all the information and send it to our treasurer. Thank you again. And do we have either Alan or Sarge? I think that's Sarge. Our trial originally, when we didn't change the time window, from energy saving time to the regular time, he can participate. He apologized. So he has another commitment at 10, which is we just started. Yes, sorry for that, he said.
Thank you, Dr. Jingbo. Thank you very much.
Welcome.
Thank you, everyone. Thank you, everyone.
Sure. Sajid, is that you? Do you want to say a few words?
Yeah, hi, I'm Sajid Bashir. I'm the secretary of this division, and it's really nice to be here. I already spoke with Zahir, and so we'll continue talking about maybe some collaboration with DFT, and I will also look at the website that Walid was showing. He's Oak Ridge, so I'll see his website and see if there's anything that he does that we can bring in. So just one other thing that Walid and Zahid may be interested in, I'm also the co-editor of a book that will be published in January 2022 by Elsewhere on sustainable energy. And so we're looking at bringing in young people, people who are not really well established yet, as co-authors. And so this book is like 99.9% done. We have 25 authors, and we really wanted 20. But there's still maybe an opportunity for somebody to come in and talk a little bit about a technique that we haven't covered so far. So I will look at the Oak Ridge website for Walid and reach out to him directly and tell him what we plan to do. But even if this book doesn't involve the people here, there's opportunities for them to be involved in a second book that my colleague is doing independent of me. So we have two books. I'm in charge of one and she's in charge of the other one. So there's always opportunities for people. And I think that's good. That's good for many, many reasons, professional, also immigration reasons. So if you want to immigrate to the US, you need a visa. Having a lot of publications in the area definitely helps with the visa. At least that's my experience.
Thank you, Sajid. Yes, thank you, everybody. Anything to say? If not, let's say goodbye and enjoy your weekend. Take care, everybody.
Thank you, everyone. Thank you, Alan. Thank you, everyone.
Thank you very much.
Thank you.
Thank you, Wenhao, for your wonderful talk.
Thank you, Dr. Phil.
Great, yeah, wonderful, wonderful. Bye.